guess we arrived to dark matter candidates. I guess, no, this should come here, no? No, I think maybe it was in, wait, yes, no, it's working. It was in Francis' computer. Okay, so, right, we arrived to this, the dark matter, yeah, it should be there, and it's some new fluid. And so what are then the ideas that we have? I hope it's not too much of a jump from showers to dark matter. Probably you need to recalibrate a little bit. But yes, thank you. Thank you. But okay, so last time, yeah, I did not put now an introduction, but we talked about dark matter, and now we like what it can be. Now is the question, okay? And so somebody asked me about the favorite models. About the favorite models. But yeah, as you can see, there are many, many ideas on the market, okay? So you probably have seen this plot already, but it basically shows, wait, here is the energy in electron volts, okay? So here it would be TV sort of weak scale. Here is like 10 to the minus 20 electron volts, so like tiny, tiny, tiny energies or masses. And then if you go on top, it's in kilograms, because somehow you hit the Planck scale here, and then you start to go to macroscopic objects, like 10 to the 10 kilograms, 10 to the 30 kilograms, which would be a solar mass, and above. And so basically, this is to say the dark matter could be, in theory, anything. I mean, we still did not constrain much this space, okay? But broadly, it could be particles, okay? Then if you go to very tiny masses, I mean, it's always this duality between particle and wave nature, but at very tiny masses, the broad wavelength of those particles become like parsecs, kiloparsecs. You know, the wave nature of dark matter would start to play a role in cosmological behavior of dark matter. So basically, right, you could go for such a tiny mass particles that are basically waves, and axions and axion-like particles are sort of in that ballpark. Then you can go to, you know, weak scale-like, and this is what we will be talking about, these thermal dark matter particles. You have stellar neutrinos, other models. And then also there are these possibilities that are not, I mean, that are heavily constrained, but not fully excluded probably, that maybe some macroscopic objects could be dark matter, okay? And people typically talk here in terms of primordial black holes, because as we talked before, we were saying they shouldn't be baryons. They should not be, we have constrained the amount of baryons from CMB, from Big Bang nucleosynthesis that we talked. So it's not that you can have baryons like those that participated sequestrated necessarily, but you could have primordial black holes, which would be like in the early universe. Let's say that in the early universe there was lots of power on some scale, on small scales, and somehow you produced some black holes very early on in the universe. This is the idea. I mean, it's not so clear how that would happen. You really have to put lots of power, lots of perturbations on very small scales, but it's not excluded. But if that would be the case, then you would create these primordial black holes, and then those would just hang around. I mean, they could evaporate and stuff, but for some mass ranges, they would just hang around, stay around until today, and those are not excluded in our dark matter possibility, dark matter candidates. I mean, this is all just to say that, you know, pretty much, since we never detected any signal that is not gravitational, people came up for models in all of these mass ranges that could satisfy, we talked here, dark matter checklist. So if you just have this checklist, particle physicists and astrophysicists were creative enough that more or less in all these 90 orders of magnitude come up with plausible candidates that would be stable, neutral, all these things, okay? And so, right. And then if you focus more or less on this particle field parameter space, here is also this famous plot from Tim Tate that shows various particle physics models. So for example, you have supersymmetry, extra dimensions. I don't know how much skilled in particle physics you are. It's not necessary, you know, that you know what it is, just that you see that it's many ideas, okay? So there are people working in all these various fields from particle physics point of view, and all this exists. If you want to think in terms of gamma rays, broadly, as also Elisabetta was saying, gamma rays can be used to probe sort of this part of parameter space, which broadly corresponds to so-called thermal dark matter. We'll talk about this. So I will focus the most on this, okay? While axion and axion-like particles broadly fall here, and this is something that Manuel will cover, okay? Then you have these other models that are like sterile neutrinos. You use X-rays for that, or asymmetric dark matter. Let me not, I mean, you can ask me questions about this, but typically you do not use necessarily gamma rays for those models over there. Right, so this is what I was saying, like WIMPs or axions. Primordial black holes also can be used. Shall I admit? Primordial black holes also can be tested with gamma rays, but I will not be talking about this today. At least I thought I don't have time. We'll see. If I'm very fast, maybe at the end I won't have time to mention that. All right. And so how it works is basically that, so of course you cannot just go, I mean, it's hard to go random. You have to devise your search strategy. So what we were doing so far is to search under the theory lamppost. So we have from theoretical side motivated some ideas, and then we look there. Okay, obviously it's not exhaustive, but I mean, it's just a place to start. Okay, and as I was saying before, one, for example, some clues, like what clues can we take from its nature, okay? One is this, that it is stable. So it's strange that it is stable. So if it's stable, I mean, it needs to be cold, it means it has to be heavy. If something is heavy, it's naturally the case to lighter particles, and so why it is stable? Ah, yes. Ah, we changed the screen. Okay, yeah, sorry to people on Zoom that it was not shared before. And so, right, so one clue is this, that is stable. So any model that you come up with, it has to respect that. Particle physicists typically impose some kind of symmetry to prevent dark matter from decaying, but imposing symmetries has consequences, and so you have to make sure that your model works in that respect. Another clue is the abundance of dark matter. Okay, because we know how much dark matter it is today, that we have today, as we said, for example, through CMB measurement. And then you have to produce, all your models have to be such that they can, for normal range of parameters or in more or less natural way, explain this abundance of dark matter. And so for so-called thermal dark matter, abundance is set through interactions with other particles that are in the thermal equilibrium in the early universe. And this is something we will be talking about now. And for non-thermal decoupling, as ALPS, axion-like particles, you have different mechanisms, such as misalignment mechanism for axions, some phase transition, reheating, and things like that. So, right, so again, I will be talking about this thermal decoupling in this lecture, and then Manuel will be telling about this non-thermal decoupling, I assume, because that is relevant for axions. Yeah, so I will now go to thermal. I just want to say that another, for example, the third clue that I did not put here because it's a bit going outside of the scope here, but the third clue would be that it's also funny coincidence the dark matter abundance is 5 times that of baryons, of normal matter. So this is a bit funny, because if dark matter and baryons would be completely different beasts that never interacted, why it would be 5 times? It could be anything. 5 times seems almost like comparable, like double or something. And so there are these models that I mentioned here, this asymmetric dark matter, they are built on that fact, trying to explain why dark matter has densities, abundance so similar to baryons. and things like that. Okay, so I'm just telling you how we are sort of building this theory lamppost based on few clues that we have about dark matter nature. Okay, now talking about thermal dark matter and its abundance. So what is thermal decoupling? So how many of you had cosmology as a course? Many. Okay, so I don't have to go in much detail here. Basically, what I wanted to stress here, so you all know, I mean, maybe I'll just start here. Okay, I'll lose this figure. So the point is that, as you know, and as it happens to many particles in the early universe, I mean, to many epochs, many events in the early universe, we explain through this thermal decoupling. This thermal decoupling is based on the fact that you have particles, you know, be it dark matter, but could also be neutrinos or anything else, that interact with a particle, with the thermal plasma, all other particles that are present in the universe at that time and that are in equilibrium. And so if it would be dark matter, we hope that it interacts with itself and somehow with standard model particles. And if it would do that, then at some point, we also said dark matter should be non-relativistic. So we expect that at some point, when universe is very hot, the dark matter particles are relativistic. Then they become non-relativistic just because the universe cools down below the temperature of the dark matter particles. And then at some point, their interactions become slow enough that they fall below the expansion rate of the universe. And basically, they stop interacting because their abundance is so low, they cannot find each other anymore in expanding universe. And at that point, they don't interact, they do not self-annihilate, and their abundance is frozen in. Okay, so this is this general idea. I have here a few lines of calculation about this, but I guess you are well aware of this. I mean, just to sketch how these calculations go, just to remind you if you forgot. Basically, how it works, that we know that what are the main ingredients? That annihilation rate for identical particles is basically proportional on the number density of those particles because they have to find each other, and on the cross-section, which is probability that they will interact, okay? So this is interaction rate. The number density, n, of particles, then is given by, so the number density of the change of number density of particles as the time goes on is then given by how many particles are produced. This is this sigma Vn, but also is given by the expansion rate of the universe. So if universe would be static, then dn over dt would be equal to this part here. But since the universe is expanding, this also affects the number density of particles. Basically, the volume is growing. And so then you have this Boltzmann equation, and if you want to find the number density of particles in the expanding universe, you have to use this Boltzmann equation. And so this equation you find for particles that are sort of, for any particles, but you know that particles in equilibrium have particular form for the number density that for non-relativistic particles is given by this formula. Okay, so I don't want to dwell on this. I guess if somebody does not know much about this, I can maybe explain later. But the point is that if one goes to this equation, it basically only sets the condition that wants to find out if my particles would be interacting in this way, at what point they would basically stop interacting, at what point the interaction rate of these two particles will become lower than the expansion rate of the universe. Because at that point, then they could not be annihilated or produced anymore. And I would have set amount of dark matter in the universe from then on. If I want to ask when this moment would happen, I basically set this condition. So this is interaction rate among the particles equals to expansion rate of the universe. I guess you're all familiar with this H. This is Hubble constant or Hubble parameter, which is the equivalent to expansion rate of the universe. And when you set this condition, you can then walk back and answer the question, so when, at what temperature this happens, at which temperature in the universe this condition is satisfied. This temperature you typically rewrite in terms of mass over temperature. You just introduce this new variable. And when you solve it, you see that this happens, that this x happens, that this x basically depends logarithmically on cross-section and on mass and on Hubble rate. So basically, once when you, I mean, it's not horribly sensitive to all these parameters. All these parameters set order of magnitude when it will happen, but it's not horribly sensitive to those parameters. Okay, and so then you know more or less, I mean, you know the condition, you know when this x, how this x generally depends on the parameters. And you know what is the number density of dark matter with respect to baryons at decoupling. Because this, how much dark matter you had at decoupling is basically equals to dark matter abundance today. I mean, when you, in co-moving coordinates, when you factor in the expansion of the universe. So you basically know how much dark matter you have over here. Okay, this is measured. And so having this as an input, something is measured, you can find what is the freeze-out temperature of your dark matter species, and you find that it is related to sigma v in these terms. Okay, and then if you assume that this interaction cross-section is in some form given like this, something like weak interaction. In a sense, you just say, my interaction, cross-section, has coupling, obviously, like Fermi interactions. You have to have coupling, how your dark matter couples to standard model particles. You just have dimensionless coupling of that, divided by the mediator mass. This is just the simplest generic formula that you can write, like dummy thing, back of the envelope. And if for this mass, you assume that is TV, because you assume the cross-section is weak, like really weak W or Z boson-like interaction. If you plug these numbers there, you find that your decoupling temperature, XF, is 25. So X is defined as mass over temperature. So you basically see that dark matter should decouple at temperature that is 25 times, that is mass over 25, dark matter mass over 25. This should be the temperature. So say if it's 100 GeV dark matter, it should be 5 GeV, the temperature where it decouples. And you see that, is it shared? Again, is it now okay? Okay, good. That it decouples of this 25 times the mass, and that cross-section, then you a posteriori sort of make sure that your assumption that sigma v is weak-like works, and in fact you can calculate more precisely the number, you get something like 2 times 10 to the minus 26. Okay? So anyway, so this is just, this calculation just shows that basically by assuming thermal decoupling, you see that it works, sort of that for weak-like cross-section, you can get the correct abundance of dark matter without much messing around. It just comes out like that, okay? So this is one of the arguments why, as you were asking me before, why this idea of thermal dark matter is very nice. Like if one would bet on something, I would say, look, this sounds very natural. So one would think that dark matter should be made of thermal dark matter, of thermally decoupled particles. So I want to just, again, if you studied cosmology, you know also that this thermal decoupling, this is not something weird, like that we now invented for dark matter. Basically, everything decouples thermally in the early universe. And one of the best examples is this cosmic neutrino background. So we know that neutrinos are also particles that were, like dark matter, interacting with all other particles in thermal bath, in thermal plasma, okay? They also, as we assume for dark matter, interacted with weak interactions, with thermal bath, okay? The only difference is that neutrinos were relativistic when they decoupled because they're almost massless, while for dark matter we assume it's massive, okay? But we know, so to repeat, we know neutrinos were there in the early universe. We know neutrinos interact with weak interaction with standard model particles, and we know that neutrinos decoupled at some point, and that now we have around us this thing that is called cosmic neutrino background. I don't know if you remember that from your cosmology class, but at some point in the early universe, actually around MeV energies and around 1 second after the Big Bang, neutrinos decoupled from the thermal plasma and are now all around us, okay? And so just that neutrinos have very low mass, so the amount of these neutrinos that are around us is not enough to explain dark matter. But this thing sort of is deeply into our cosmological model, so we believe neutrinos just decoupled like that. And so it's not such a crazy idea to assume, okay, and so if there was some particle extremely similar to neutrinos, only was non-relativistic, you just do the calculation and you get, look this, like if this would be true, then you would get something that is 5 times more abundant than normal dark matter. So it's really weird. I mean, it sounds really convincing that this is something completely natural to have happened. Okay? All right. Right, so this is more or less saying this. So in thermal scenario, you assume weak scale annihilation and naturally explain the abundance of dark matter. But then this is suggestive of new physics not too far above the weak scale. And so here is the problem, because we still did not discover new physics close to the TeV scale. So this might be one of those models that sounds so nice, but then nature, just ain't true. Or it just might be like, patience and might happen. So let's see. But anyway, so it's very natural, however, not yet a signal close to weak scale. So now we are getting above TeV. So how far from weak scale is far enough or far too much? But okay, we still, of course, did not explore much above weak scale at LHC or anywhere else. So it's not yet that we are orders of magnitude above, but still would be nicer if we would have seen it already. Let's put it in that way. All right, and so what I will be talking about is this. So then this chunk of models that is thermal dark matter, and that you assume that you have basically, as we said before, the two dark matter particles interact somehow with standard model, self-annihilate, producing standard model particles. Standard model particles then decay to stable standard model particles like photon, neutrino, or charged cosmic rays. You assume in this thermal dark matter picture that this all happens around the TeV scale. So basically, then you basically use experiments that look around TeV to 10 TeV, 100 GeV, 100 TeV, like TeV plus minus 2 orders of magnitude scales. You look for extra emission in these particles and hope to find your thermal dark matter. So this is the name of the game. All right, and another thing, extra bonus, is that more or less you know at what fluxes you're expecting. Because in these thermal scenarios, we said that this is more or less fixed. And so, right, so this is the game. You look for those particles at around TeV scale, give or take 2-3 orders of magnitude, but you know at what cross sections you're looking for. Okay, so then experiments, okay? So how do we look for those? So most of this was already covered a little bit with, by Elisabetta and Franz. I will just put it a bit in the context of dark matter search. Like I will underline what is relevant for dark matter search. So as I said before, you can look in gamma rays, in neutrinos, in charged particles, okay? All of these can be also primordial black holes are expected to emit such signals. So be it thermal dark matter, ALPS, or primordial black holes. And in general, signals, flux that you expect. So now we do not see the upper line, but the point is that the expected signal, this is in neutrinos and photons. Okay, doesn't want to disappear. Anyway, never mind. It wants me to see the chat. I see. Okay, good. Yes, thank you. Thanks. Good. All right. Yeah, so I just wanted to say this. Like, so so here there are these sort of three oh, now I have to touch the So as I was saying here, so if you have these neutral messengers like photon and neutrino, and then you have charged messengers as charged cosmic rays. So for neutrino and photon, they travel in straight lines. They're not charged. They don't interact with magnetic fields that we have in the galaxy and in intergalactic space. And so basically, for photons and neutrinos, as those are messages that travel in straight lines, you have basically maps. You know where your messenger came from, and then and therefore your flux depends of cosmology, in a sense, like how much dark matter you have along your line of sight. I will tell you more about this later, and depend also on particle physics. So particle physics will determine the shape, the spectra of gamma rays and neutrinos that you expect, okay? And then if you're talking about charged particles, then it's a bit more complicated, because charged particles, even though they're produced at some point, they got, travel through galaxy for millions of years, depending on energy. Either they remain trapped in the galaxy, or if they're extragalactic, they have to come to you. But in any case, you have to, you do not get signal directional, but you have to modulate it with other astrophysics of their propagation. And so basically, for charged cosmic rays, you have only fluxes. You don't have images, 2D images, but only spectral fluxes. So I will not be talking about this. I will just focus on gamma rays right away. But just to say that if you have charged particles, then, so here everything is normalized together. But typically, you will see later, typically for charged particles, you look for antiparticles, because antiparticles are not produced so much by by background. You don't have so much background in antiparticles. So in this case, this is your strategy. But putting that aside, let's just focus on gamma rays. Okay, so this is the plot that Franz was saying and somebody was asking. So I will tell you now. First, so why gamma rays? So positive sides, pros, and they're neutral and they point back to their source. They're easier to catch than neutrinos, so you have more gammas than neutrinos. This is nice. But challenge is that still you have much less gamma rays than charged cosmic rays. This is what Franz was saying. So for example, this is again Fermi energies up to 100 GeV, but if these are protons, charged protons, then you have helium, you have electron, then you have anti-electron, and only here is gamma rays. No, sorry, okay, positron, right, and only here is gamma ray. Okay, so you see, as Franz was saying, sort of 4 orders of magnitude, you have to beat all this cosmic ray background in order to measure gamma rays, which is a challenge. So, but challenge then addressed experimentally, as you will see. And right, and so now if you're talking about which tools, this is something covered by Franz. I will put it also here, sort of repeat. You have these different gamma ray instruments as you move forward in energy, okay? You have Fermi-LAT as a satellite, then you have these imaging Cherenkov telescopes in hundreds of GeV to tens of TeV range dominating. Then you have water Cherenkov like Hawk going to hundreds of TeV, and then we are entering in PV domain with LASSO and Tibet array. So what is relevant for Fermi, for these energies? I mean, this will determine a little bit the analysis strategy then later when we look for dark matter, is that for Fermi, again, as Franz was saying, you have large field of view, so you see the whole sky, basically. But what is very important is that here you'd have quite negligible cosmic ray contamination. So why is that? So again, we have, for every 10,000 protons, you have 1 photon. So you have to cut this background horribly. But Fermi manages to do it because it's in space, and it has this anti-coincidence detector, the yellow thing. So whenever a charged particle passes through, it tags it. And so basically, you can directly remove all I mean, to great extent, all charged particles that pass through Fermi. So you have very clean gamma ray sample. Okay, you don't have to worry so much about cosmic ray contamination. And this helps a lot when you do the analysis of extended signals. I will tell you about this. But when you look for dark matter, this is very important. But of course, it has limited effective area because you cannot send huge things in space. So this is just 1 meter cube. You cannot do much more than that. And it has a bit limited angular resolution. For Cherenkov, imaging Cherenkov telescopes, right, you have huge effective area, you have quite good angular resolution, but you have limited field of view. Again, this is not ideal for dark matter searches, depending, but it's a bit of a challenge sometimes for dark matter searches. And then you have significant cosmic ray contamination because, as Franz was explaining, it's very hard. I mean, it's being done in with amazing precision, but still there is quite a bit of cosmic rays that pass through cuts, and you have these huge backgrounds for photons. Hawk, similarly significant cosmic ray contamination, but it still has large duty cycle and sees like large portions of the sky. And then LASSO is this combination of many techniques. No, it has part that is Hawk-like, it has some Cherenkov things, and it has also a smart thing that it has scintillators that detect muons and help it remove cosmic ray background. So this is fancy. So it found a way, somehow like Pierre Roget would to sort of have different kind of anti-coincidence detectors on the ground to tag charged particles. But as Elisabetta was saying, doesn't have great angular resolution, and so, yeah. But anyway, so I think this is anyway great how we have all these complementarities among these experiments, so one can look for different sides and then together learn more stuff. And then of course in the future there is a CTA that will have this huge energy coverage. I will be talking about this later. So then what is the expected signals and targets where we usually look for dark matter? So for the signal, I already sort of discussed this, that you have for flux in gamma rays, that you have the part that comes from particle physics and part that comes from dark matter distribution, okay? Part that comes from particle physics, basically, again, cross-section is something that you want to determine, cross-section mass. But this is something that you have to put in your analysis, what spectra of dark matter you expect. And that spectra, sort of luckily, you do not have to know much about dark matter nature to know this spectra, okay? Because how it would work is the two dark matter particles would somehow annihilate and produce some standard model particles, but from then on, you know the physics. You know that your Ws or quarks will produce pions, and pions will decay and will produce gammas. And so basically, no matter which channel, you typically get very similar spectra for all channels that your dark matter would produce. And that spectra has this bump, sort of pion bump, that is typical for, it's not just a simple power law that is then typical for dark matter search. What happens in some dark matter models, it's not so often that you would have significant cross-section to these channels, but this is amazing signature for dark matter, is that at some cases dark matter through loops could annihilate to 2 photons, okay? We said before the dark matter does not have charge, so it does not produce photons directly. But if you have some loop-like interactions, it could produce 2 photons. And in that case, you would have a dark matter line. That would be your signature. Or if dark matter annihilates via intermediate state, it annihilates to 4 photons, then you could have these box-like signatures. Okay. So I'm just saying, like, if generically you're looking for dark matter, you look either for some rather featureless spectra like this, or you could look for particular models for like spectral lines or sharp cutoffs. This would be something that dark matter can produce. For astrophysics is not so easy, so it's a sort of a signature. Is a signature of dark matter feature. So now if you're talking about the distribution of dark matter, for that we have to, so of course we do not see dark matter, we have to look at tracers. So either we look at tracers, as I said, stars or something that follows gravitational potential of dark matter, or we resort to n-body simulations. We just simulate how dark matter should interact gravitationally, and we draw conclusions from there. And so now, what is this dark matter density map, dark matter density distribution that we, expect it's there, and will determine where to look, like where our signal should be the highest. Okay, so if you look in dark matter distribution, so this would be like Milky Way halo. Again, I assume you're all familiar with that our Milky Way halo of our galaxy, say, it's sort of 200 kiloparsecs large, the virially connected part that contains the dark matter halo, while the Milky Way spiral arms, and what we see is like sort of 30 kiloparsecs large. It's a tiny thing sort of in the middle. So basically, again, like all this is dark matter map, and there are just spiral arms overlay with that. But so the color here tells you where dark matter is. So one place to look then is the center of our galaxy. You see that in the center of this halo of the Milky Way, you have the most of dark matter. Okay, and so basically, this is where this sort of place for dark matter signal should be the strongest. But notice that signal is extended in the galactic center. So if you look for dark matter in the galactic center, it wouldn't be like a point source. You would really have to look at a region that is at least 10 degrees around. Okay, this is where you would expect it to appear, and you would expect it to be extended. Okay. Then, if you go now, if you see all of these little points dot here, you see that in simulations you find a lot of dark subhalos, a lot of substructure of smaller clumps of dark matter that are present in our galaxy. So here I show the mass function of such halos, like how many halos of a given mass you expect. Okay, so you see that here is 10 to the 8, 10 to the 7. You see that to smaller masses you go, more and more of these halos you have. And so basically the numbers here are huge, and they're dominated by small objects. The small subhalos of 10 to the 7 solar masses or less are too small to have any stars and any gas. So basically those would be just concentrated dark objects that are expected to be there based on N-body simulations. Then if you go to a bit bigger of these subhalos, you arrive to these dwarf spheroidal galaxies. So those would be objects of 10 to the 9 solar masses or so. Those are subhalos of the Milky Way predicted, but they're big enough to have some stars. So those we can detect, faint stellar overdensities, and we know then where those dwarfs are, and then we could look for dark matter signal from them. So they have, as I said, mass 10 to the 9 solar masses or so. Then there are Magellanic Clouds. So these are irregular galaxies in our local group. So they're bigger. They're 10 to the 10 solar masses or so. And they have the bar. They have lots of stars. We know very well where they are. So we could look. Should we admit? Okay, I could do it. I thought you have it on your... you could look in those objects for the signal. You think it's okay? Yes. Yeah, it's working. Thanks. Then we could look further in our local group. That together with Milky Way in the local group, we have the two galaxies M31 Andromeda and M33. So Andromeda is like the bigger sort of sister or brother to the Milky Way. This is a huge object, few degrees on the sky, and we could look, and it has a lot of dark matter. It's even larger than the Milky Way. So we could look in Andromeda or triangular galaxy M33. And then going out, here is the local group. We have clusters of galaxies that, as we know, have tons of dark matter, and we could also look in gamma rays. Gravitationally. They do orbit. I mean, yes, exactly, through their motion. And they're also close enough. We could also know through the gravitational potential that they're close enough to escape. We'll have more. Yeah, good point. Yeah, through motion, like always in gravity. You only have mass and motion to determine. But yeah, so there is local group, and then galaxy clusters like Coma, Virgo, Fornax that are around us. okay? And then going even further, so this would be, as I was saying, like if this is a Milky Way and some galaxy clusters, you can look, from our perspective to annihilation, say, of dark matter in all cosmological structure all around us. People also looked into that. I will also tell you more about this later. So basically, the answer is anywhere that there is dark matter, in simulations, you can look and people have looked. But I wanted to stress here what are the main uncertainties in dark matter prediction. So there are some uncertainties related to particle physics, to the spectra. They're typically not so significant in this moment before we have a discovery. If once we have a discovery, we'll start to worry about precision on that front. But the bigger uncertainty is on dark matter distribution. Because that one we really do not know to huge precision, and I will tell you why. So basically, as I said, we get a feeling about the dark matter density distribution from n-body simulations. It's a one way, but so this picture shows the actual measured dark matter distribution, galaxy distribution, and dark matter distribution from simulations. Okay, and we see that at large scales, these look very similar. So basically, n-body simulations are very precise in large scales, megaparsecs scales. But on very small scales, they lose precision. I will show you more, because you cannot, it's very hard computationally to simulate self-similar processes on every scale. So if you have to put basically you're limited by amount of dark. So how n-body simulation work? You put dark matter particles in, but you don't put dark matter particles like each particle. So dark matter particles are something like that is 10 to the 6, 7, 8 solar masses. Because if you want to simulate, the universe, the large box in the universe that is, contains hundreds, thousands of galaxies, you cannot have enormous number of particles in your simulation because you will run out of memory. And so each particle in your simulation is very heavy. And that means that you cannot simulate, if your unit in the simulation is 10 to the 6 solar masses, of course you do not know what happens at smaller masses or at smaller scales, because that also means that you cannot really resolve something that is, very tiny if your particles are huge in the simulation. So basically, right, so this is the point. So we have good simulations, but due to computational power, they lose resolution on small scales. And so basically, if you're, so if this would be Milky Way, and you are, sort of measuring, so this is your simulation, you're measuring what is dark matter density as they move closer to the galactic center. So at high distances, all simulations agree and you measure them very precisely. But as you come closer to the galactic center, you basically have to extrapolate. You do not, this is like your resolution is huge. Like this is your box of resolution is hundreds of parsecs or even kiloparsec large in your simulations, just due to computing power. And so we do not know and can just do some educated guesses for extrapolation. And as I was saying, we do not resolve much smaller masses just again because our unit mass in the simulation is something like this or bigger. But this is something I did not say, what we expect, even though our simulations can go down, say, only to 10 to the 5 solar masses, in theory, we predict dark matter subhalos down to 10 to the minus 6 solar masses, like Earth mass subhalos. And so this is prediction, and this is where we stop with simulation. So it's obvious that there is huge uncertainties here. It's obvious that you have to extrapolate, and whenever you extrapolate, you don't know. you by definition do not know what you're doing. Okay, another thing, another elephant in the room here is that simulations as well, in large part, are dark matter only. Like we do not have all this computing power or knowledge to include interactions of baryons. The idea is that on large scales, typically, well, this is true only to some point, but at large scales, you're dark matter dominated anyway, so whatever baryons do doesn't matter, it's not important. However, at small scales, in the galactic center and small subhalos, the so-called baryonic feedback starts to be really, really important. Because as you you know, in dwarf galaxies, say, if you have lots of supernovae going off in short period of time, they can inject enough of energy to sort of disturb dark matter distribution and change it and get rid of dark matter. Or in the galactic center, if you have a so-called AGN feedback, it can also change the profile in the galactic center. And I mean, there is lots of progress. So it's actually amazing what simulations with baryons are doing nowadays. They can really, like early on, like maybe even 10 years ago, what you get from these simulations was nothing like real galaxies. Now they're approaching the good precision. But again, small scales are always a problem because it's very hard to do it on every scale. But anyway, so so resolution is one problem. Second problem is that we do not really very well how to model baryonic feedback, and that one also matters a lot at small scales. So it's always very uncertain there. How about observations? Again, observationally, in galaxies, in clusters of galaxies, we know how to measure gas, stars. We more or less know what is gravitational potential. But as you go to dwarf spheroidal galaxies, you see this plot shows you the dwarf. So this is the distinction. So this is brightness versus the radius of the object. And here are dwarf spheroidal galaxies. They typically have 1 kiloparsec. They're 1 kiloparsec large. So-called classical dwarfs, if you have around thousands of stars, okay? So this is where dwarf spheroidal galaxies live. And globular clusters, these are objects that are very bright and very small, 1 parsec or so. These objects do not have dark matter. It is not clear so much how come these guys do not have dark matter, but it's believed that they sort of got stripped of their dark matter content. So even though they have the similar number of stars as dwarfs, they're just much more, yes. 5 minutes. Already. I thought I would be faster. That these guys do not have dark matter at all. And so why I'm saying this is that with dwarf spheroidal galaxies, you can determine you can find them, first of all, if they're big and have lots of stars. But as you go to fainter and fainter objects, you become to confuse them with globular clusters. It becomes harder even to define what is a dwarf galaxy and what is a globular cluster, and even less so to know what is the dark matter content in them. And so this is sort of reflected also in this point, that if you have luminosity of a dwarf galaxy and reconstruct a dark matter mass, so you see that in these classical dwarfs where you have 10 to the 6 solar mass luminosity, where you have lots of stars, you can reconstruct how much dark matter you have due to the motion of those stars, velocity dispersion, with quite small uncertainty. But then if you go to very faint objects, uncertainty just blow up. Okay, so this is again to say that for small subhalos and small here is 10 to the 9 solar masses, already there you start to lose your observations of how much dark matter you have. And so right, so these are the challenges that we face here. Also from observational side, if you go to the galactic center, say this is our galaxy, this is 0 to whatever, 30, 80 kiloparsec, Earth is here. And so you see that outside of Earth radius, even observationally, this is the total total velocity, observed velocity of stars. And here is written like which component contributes the most gravitationally to this rotational curve. And you see the dark matter dominates gravitational potential only after 10 kiloparsecs or so. So only after 10 kiloparsecs, the motion of stars is due to dark matter. And there you directly, by measuring velocity of stars, you measure the profile of dark matter. But if you go in towards galactic center, the mass of stars in the bulge dominates the gravitational potential. Dark matter is subdominant. So you measure velocities of stars, but they're determined by stars themselves mostly. And so then you have huge uncertainties on what is your observational density of dark matter. Okay, it's always the same thing. So this is sort of in a nutshell summary of this little part, that we use n-body simulations and observation of dark matter traces to track dark matter density profile, but at small scales we fail, both observationally and in simulations. So let me see. So this is the stop. I was hoping I will start the other lecture, but 5 minutes you still have or not? Few minutes, or Or maybe, I don't know, maybe we can stop. You guys are exhausted. Very happy. Poor guys. Okay, okay, then let's stop here. I don't know if you have a question. Oh, yeah, wait, we should maybe.
Thank you. I have a question about this core cast problem. Considering what you said, that first, well, in my understanding, the core cast problem is a mismatch between the observations and simulations at the center of the galaxy. But on one side, you said that we don't know very well or we cannot resolve with simulations what is going on in the center. And on the other hand, we don't know very well also from observations. So I don't understand if this missing, missing satellite, the core cast problem is a real problem after all.
Okay, so it depends whom you ask, exactly. Right. So you're right that depends how you exactly also you ask a question, okay? Say, I mean, in general, what I said, it's true that in general you do not know much, and one should not make very strong conclusions about the part of parameter space where one has huge uncertainties. This is true. I mean, those core cast problems and problems is like too big to fail, missing satellite problems. The statement there was that it's true. So I think the statement used to be is that it's true that we do not know so much, how many small satellites we should have. Say, because for smaller satellites, maybe they got disrupted, maybe they don't have many stars. So the fact that we do not see so many satellites might be that we just do not observe stars or they're not there. But then the problem was rephrased like as too big to fail. That there is even for the biggest dwarfs, for which we should know, and for, so maybe let me just go here. Wait, which direction I'm going? Just a second. I think is the best illustrated here. So, okay. So this is the number of dark matter subhalos that you expect as a function of mass. Okay. So what I was saying is that for small subhalos, you do not know very well, how many you have. But then the statement was that even for these, the biggest subhalos, for which baryonic feedback should not play such a big role, even those you have less than you would expect. Okay, so how serious is that problem? I do not know. I mean, in a sense, like it depends whom you ask. I think it a little bit went away, this controversy, too big to fail or core cast, but it is understood sort of as potentially resolved by baryonic feedback or problem simulations. Yeah, but it was always rephrased in these terms that it's true that there are uncertainties, but in this part of parameter space, uncertainties are not so large, there might be a problem still. Mm-hmm. Yeah.
And can I, about the paradigm of, here.
Who are you? Because I heard from there.
Can we say that cold dark matter paradigm is better than warm dark matter paradigm?
Is better. Well, okay, so again, good question. In a sense, like, again, depends. Like, so very warm is excluded because you have, as I was saying before, because it would not give you enough substructure, okay? On the other hand, mildly warm, like I forgot how they call it, mildly warm, is not excluded. And then some people claim it might be better because it predicts less satellites more in line with what you observe. And so I do not know. I mean, to me, it's huge uncertainty there. Like warm dark matter predicts less satellites, but do we observe less satellites because we have observational bias, because there is some baryonic feedback that we didn't take into account, or because dark matter is warm? It's not, to my mind, is not clear. So it could be either. So for me, cold dark matter is good. Warm dark matter might be. I mean, mildly warm dark matter could still be an option. Yeah.
Okay. Thank you.
Yes, I have a question regarding the difference between the dwarf galaxies or dwarf spheroids and the globular clusters, which is, I think, very,
it's
very
curious.
nice. It is just for the dimension, or
Well, the point is that they're very different objects in a sense. So globular clusters are extremely dense objects, no, and they're full of pulsars, millisecond pulsars, because they have all these binary systems, and they actually shine quite bright in gamma rays. White dwarfs are not discovered in the gamma rays at all. So dwarfs have much less baryons and much more dark matter. But I think, and the difference between them is probably formation. Probably they both started as normal dark matter dominated clumps, and somehow idea is that the globular clusters maybe in passing through the galaxy got stripped of dark matter content, and then only the dense core survived, and they are now just very dense, stars. But yeah, it's fascinating that they are very similar in a sense in star content, but extremely different objects.
And the ultra faint, what are they?
So ultra faints are those that have very few stars. They're very, very, how should I say, very faint when you observe them. And so often you cannot even tell very well what is their extension, or you cannot tell how much dark matter really you have. And then, because difference also between globulars and these are that these do not have dark matter. Like their mass is really what you see. Okay. And so then there is this confusion region.
Okay.
Yeah, yeah.
Further questions? Yeah.
So when you were showing your calculations for the mass and the cross-section of the dark matter, it showed the dependence on the Hubble parameter.
You mean the freeze-out?
Regarding the Hubble tension, does the difference between the type 1a and from the Hubble from the CMB, right, does it have a
significant impact?
Yeah.
No, no. In this case, good. I don't even know where it was. Okay, so all right. No, not really, because as we were showing here, like basically everything depends logarithmically, and so Hubble tension is between 70 or 80, or like it's tiny. Here we are really playing with orders of magnitude that matter. So right, for this calculation is not. Thank God. Also, that uncertainty we don't worry about.
Okay, thank you.
Yeah, thanks.
But I should say that H might change a lot from lambda CDM beyond lambda CDM.
There is
Well, you have said about freeze-out, but there are some alternative scenarios.
Sure.
When we have freezing. So I want to learn a little more about the scenarios. How is the mechanism in it?
Right. So this is very limited. You're right. Would be nice maybe to expand here. So here the idea was that we assumed the dark matter was in thermal equilibrium and then went out. For some dark matter models, your dark matter particles are so feeble interacting that they're actually never in thermal equilibrium in the early universe. So they're just like standalone particles over there. Then somehow they could, as the universe cools down, their densities. I forgot now how these models go. Yeah, now I forgot. Ah, yes, go ahead, I forgot. Yes.
Dark matter yet, or you're gonna have a very small abundance of dark matter at that point. Sure. So this line will increasing as the time is passing and the temperature is
because they're being produced,
falling.
right? Exactly, they're being produced to some mechanism slowly, and they're building up the density, right? That's part that I forgot.
At the end of the day,
and then at some point they would just, be enough. Their abundance would be enough that they would start to interact and to be present in the thermal equilibrium. And right, so I mean, there are also other. Let me just think. I mean, there are different ways how you could. I mean, then there is this that I was mentioning, this asymmetric dark matter. The asymmetric dark matter would be related to baryon density. So basically, dark matter would have the charge, would have sort of baryon number itself. And so as if in our universe we have particles and antiparticles. So you know that for some reason we have only particles in our universe and all antiparticles disappeared in some point, no? And the idea there is that this baryon number got transferred to dark matter sector, so that all our world has all the baryon number and all the dark sector has the anti-baryon number that would sort of be equal to ours. And so their mechanism for production is different in a sense, like it proceeds, again, I don't know where I'm going, but it proceeds in such a way that dark matter annihilates with anti-dark matter up to the point that net charge equals to the part. So in our world, we have as baryon number excess, and in dark matter would annihilate against anti-dark matter up to the point that this anti-baryon number excess is transferred in the dark sector. So I did not explain this very well, but basically there you annihilate, you do not decouple thermally, but you just decouple when you do not have any more anti-dark matter particles enough, like in our universe. To do. So right, so I mean it's beautiful again, these dark matter searches, if for nothing for all these ideas that people had, how you can play with things and with ideas. Yeah.
Yeah, okay. Okay. Further questions? No? So let's thank the Gabri.
Thank you guys.